Welcome to Foodtech Simplified. You are listening to Areeb Irshad, and today we are going to talk about material balances in food engineering. Now, material balance is one of the most important topic in food engineering, and first of all, let us understand what material balance exactly is. So, let's say that you have a bucket. All right, so this this looks like bucket, I think, and let's say that you have some water in this bucket. Let's say you have 5 kg or 5 liter, you can also say 5 liters of water, and then there's a bigger bucket. There's a bigger, you can say, utensil or a bigger bucket. Now if you transfer this 5 kg of water into a different utensil or in a different container, then material from a container A will be transferred to the container B. And that simply, in the simple terms, that is the transfer of material. Now, as you all know that mass can neither be created nor destroyed. It can only be transferred from point A to point B. So material balance is one of the concepts that is based on law of conservation of mass. And we are going to talk about law of conservation of mass a little bit more in this video. But first of all, let us understand that why material balance is so important and what are the applications of material balance in the food industry, because I believe in the food industry, if you don't know the application of material balance, then it's probably not worth it to just know the concept. You should also know the application of material balance. So let us understand that step by step. If you ever get to visit a food plant or a food factory, you will observe that there are some certain equipment, and these equipment are connected with one another. There are maybe pipelines that are connecting these different equipment, or maybe there are some connecting medium that are connecting these different equipment. So I'm just drawing a simple block diagram to illustrate a point that in a food industry, how two components or two equipment are connected with one another and how the flow of the process is carried out. So let me just quickly mention over here that these equipment are, first of all, this is an evaporator, and let's just say for the sake of this example that this is a crystallizer. All right. Now let's say that in this evaporator a sugar solution is being fed. There's a sugar solution that is being fed in this evaporator. Now, what is the function of an evaporator? The function of an evaporator is to evaporate the vapors from a given solution or from a given liquid or semi-solid. So evaporator basically concentrates a solution, a dilute solution. So obviously, in an evaporator, what will happen? The amount of water present in the sugar solution will evaporate with the passage of time. So this is the water, or you can also say that these are vapors which are going out of the evaporator. Now obviously in an evaporator, what happens that the water evaporates and the sugar solution, the initial sugar solution which was diluted, is now more concentrated at the outlet of an evaporator. Now this is a concentrated sugar solution. All right. Now this is concentrated sugar solution which goes into the crystallizer, and I'm not going to tell you a little in depth about crystallizer or evaporator. You just need to know the basic for the sake of this video. So in a crystallizer, basically what happens is that the sugar particles or the sugar molecules become definite. They come into existence, or you can also say that they are crystallized. Now at the outlet of crystallizer, the final product is being collected. Now this is just an example, and some specifications might differ for the evaporator or for the crystallizer, but this is just to illustrate the flow of the process. The flow of the process is shown by these arrows, and you can see that sugar solution enters, and finally we have crystallized sugar at the outlet of crystallizer. So how does the material balance come into this equation, or how does the material balance applies here in this situation? Now using material balances, we can find out what is the inflow and what is the outflow. In a food industry or in a food processing plant, we are interested to know that what is the amount of feed that is going in of an equipment. So inflow is the feed that is going in, and in this case sugar solution is the inflow that is going in the evaporator. In the same fashion, outflow is anything that is collected at the outlet of the equipment. Anything that is our final product or anything that goes out of the equipment is outflow. So in a food industry, we are interested to know the amount of inflow or the amount of outflow, or maybe both of them. And sometimes we are interested to know the rate of entering of a sugar solution, and sometimes we are interested to know about the rate of final product. For example, the sugar solution could be entering with a rate of 3 kg per second, and sometimes using this value we may have to find out the rate of exiting of water or the vapor, or we may have to find out the rate of outflow. So we are interested to know about the inflow and outflow of the material in the process. Now I have just highlighted inflow and outflow because of a reason. Because inflow and outflow are important in a material balance, and if you know the inflow, because in many cases you will be required to understand what is the amount of inflow and what is the amount of outflow. Now let's mention the next point. In many cases we are also interested to know about the calculations. So the calculations are used in formulating products to specified composition from available raw materials. Now this means if we desire to produce 50 kgs of concentrated or 50 kgs of crystallized sugar, then accordingly we will have to formulate the recipe or we will have to formulate the amount of raw material or raw sugar or a sugar solution required as the feed. So we need to calculate these values. We need to apply material balance so that we can formulate the quantities of different products so that the final desired product is as per the requirements of the industry. The third point, or you can also say the third application, is evaluating the composition after blending. Now in many cases, let's say in the example, let's take the example of juice or apple juice. And so in apple juice, or maybe even a mixed fruit juice, you have to blend different components to attain the desired result. In that case, if we want to evaluate what is the composition that will be achieved after blending, we need to apply material balance equation in that scenario. Also, the material balance equations are required to evaluate the processing yield. Now, what is processing yield? So, yield is nothing but the amount of the desired product. Let's say I have processed 100 kgs of apples or 100 kgs of oranges, and finally I get 10 liters of orange juice, final packaged orange juice. Now, this is just an example. I'm not really literally mentioning that from 100 kgs of oranges you will get 10 liters of orange juice, but this is just to mention that we applied material balances to understand or to calculate what is the amount of final product. And finally, we also use material balance equations or the concept of material balance to evaluate the separation efficiencies. Now, what is this separation efficiency? Now, separation efficiency, let's highlight this separation efficiencies. Now, separation efficiencies basically tell us that how efficiently two different components are being separated. Because also in a food plant or a food processing plant, we are interested to know about food wastage. We have to minimize the food wastage. We have to minimize the wastage as much as possible. Because, or we can also recycle this waste back into the food industry. We can utilize this waste. We can find out some of the methods to utilize this waste. So what do we have to do? We have to calculate the efficiencies. We have to calculate how efficiently this waste is separated or utilized. And we apply material balance equations to understand how efficiently different components are being separated. For example, you can also see in this block diagram, here water is being discarded because obviously we do not need water. But can this water recycled, or these vapors, can we reuse them? Is it possible? Can we reuse them? You may have observed in a food processing plant that sometimes we need steam. Sometimes we need steam for heat exchangers. So is it possible to use these vapors? Is it possible to utilize these vapors once again? That would increase the efficiency of the whole processing plant. And why do we want to improve the efficiency? We want to improve the efficiency because food industries basically want to utilize their time to maximize their yield, to maximize the products, and maximize their profits in the given amount of time. So that's how. Let me also highlight other points. Calculations, formulating products. This is something that I wanted to highlight. And evaluating the composition. That's why we use material balance. We want to evaluate the composition. And also evaluating processing yield. Alright, so these are some of the basics of material balances. Let us now move on and understand the law of conservation of mass. So the material balance or the concept of material balance is based on the law of conservation of mass. Let me write this down. Material balance, or you can also say material balances, are based on the law of conservation of mass. That means, or you can also say that states, because that would be more appropriate. Because the law states mass can neither be created nor destroyed. So the material balance is based on the law of conservation of mass, and the law of conservation of mass you may have already studied that mass can neither be created nor destroyed. Now, obviously, you know that mass can neither be created nor destroyed, but how does this come into play? How do we apply this? So, in any process, let me write this one down. In any process, and by any process I mean any process in the food plant, any process in the food processing plant, the material balance can be given as the material balance, or you can also say the material balance equation. Can be given as inflow. Let me write this in a different color so you understand the importance of this. Let's choose orange. Inflow is equal to outflow plus accumulation. Let me just write this and I will explain to you that what do I mean by this equation, what does each term in this equation really mean. Let's keep this in a box so that you understand the importance of this equation. Let's do this once again. That's much better. Oops. Okay. So inflow is equal to outflow plus accumulation. Now, inflow is the amount of feed or any component or any fluids that are entering in the system. Anything that enters into the system is inflow, and anything that exits the system is outflow. As simple as that. Flow, that means something that is flowing. In means inside. That means anything that is flowing inside is inflow, and anything that is flowing outside is outflow. As simple as that. But what is accumulation? Accumulation comes from the word accumulate, and accumulate or accumulated means anything that is collected at a specific place and that is not moving in or moving out. Let's take an example and you will understand what do I mean by accumulation and how does this equation come into play. Let's take an example. Now, first of all, let me write down the simple definition of these terms. Inflow is components entering the system. Now, anything that enters into the system is known as inflow, and outflow is the opposite. Outflow is components, or the components can be fluids or material, anything. Exiting. Now in this case, this is exiting. This is the opposite. The system. Alright, so keep this in mind. Now let's talk about accumulation. I already told you about accumulation, that anything that doesn't flow out of the system gets accumulated in the system. So let's write this down. Anything that doesn't flow, that does not flow out of the system at a given time. Now, why at a given time? Because with respect to time, some of the accumulation may move out, some of the accumulation may get converted into outflow. So that's why at a specific time, at a specified time or a given time, the accumulation or anything that is collected or the accumulated material does not move out of the system. Let's see it practically. Let's illustrate an example and you will understand what I mean by that. So let me draw something. Let's draw a container. Let's use a different color. I hope I get this right. Not really a pro at using this software. Anyway, if you have studied fluid mechanics, you may have seen something like this. You may have seen something like this. But if you haven't studied, that's not a big issue, because I'm going to explain what I am drawing here in just a bit. Just have a little patience. Alright, so let's say that this is a container and it is filled with water. Alright, so this is water. We can mark this that this is water. Oops, didn't want to use that one. So yeah, this is water. And in this container you see two inlets, or you can see one inlet and one outlet. Let's assume that this is an inlet, and in this inlet material or water is flowing in. We can mention this as the inflow. Also, we can use I, capital I, as annotating to annotate the amount of water that is flowing inside of this vessel. And let's say that a specific amount of water is flowing out, and let's annotate the amount of water flowing out as capital O. That is the outflow. Now I is the amount of water that is flowing inside, and O is the amount of water that is flowing outside of the container. Now in this case, if we use mass balance equation or the material balance equation, what is the material balance equation? As you may remember, I just highlighted, this is the material balance equation. This is the material balance equation, inflow equal to outflow plus accumulation. Alright, so let's try to apply this equation here in this scenario. Let's say that there is no accumulation. Let's say that 5 kg of, oh my god, yeah, that's much better. Let's say 5 kg or 5 liters of water is flowing inside and 5 liters of water is flowing outside. 5 kg is flowing inside and 5 kg is flowing outside. So in that case, you will observe the level of water remains steady. The level of water in this vessel is constant. It is neither rising, neither it is decreasing. So in that case, you can easily see that inflow is equal to outflow. Let me write this down. Inflow is equal to outflow. And here there is no accumulation. Nothing is being accumulated. Why? Because we can also prove this mathematically. A little while earlier you observed the equation inflow is equal to outflow plus accumulation. This was the equation. And in this case, accumulation is 0. Nothing is being accumulated. Whatever is flowing inside is flowing outside. The amount of water, same amount of water that is flowing inside is flowing outside of the vessel. So nothing is accumulated. So accumulation is 0. This is 0 and this is O. Please don't get confused. This is O and this is 0. This is 0. Okay. So in this case, what will happen? Inflow will be equal to outflow. Also, this situation, this specific situation, is known as steady state. We call this as steady state. Why do we call this specifically as steady state? We call this as a steady state because, as you observed, as I already mentioned, the level of water in this vessel is at a steady state. It doesn't move up or it doesn't move down. The level is constant. It is steady. That is why we call this as a steady state. Okay, so but what will happen if the amount of inflow is altered and what will happen if the amount are differing? Now this is, in this case, in this specific case, inflow was equal to outflow, but that doesn't mean it will happen all the time. Sometimes inflow will be greater, sometimes outflow will be greater than the inflow. So let me illustrate this again with the example with a similar situation, but let's alter the values. Let's alter the values. So let's say here I have 6 kgs of water that is flowing inside, but 4 kgs of water that is flowing outside. Now in this scenario, in the second situation, what will happen? In the second situation, inflow is greater than the outflow. And in this case, when the inflow is greater and outflow is smaller, there will be some accumulation. Something will get accumulated in the vessel. So accumulation is not equal to 0, and this condition is known as unsteady state. We call this as unsteady state. Whenever accumulation is not equal to 0, there will be unsteady state. Let us take another illustration or another example. Let's erase this value once again. Now let's say that the inflow is 4 kg and the outflow is 6 kg. Now I just reverse the values. The outflow, in this case inflow, is smaller than the outflow. And obviously, if the inflow is lesser, the amount of water flowing inside is less and the amount of water flowing outside is greater, then the level will decrease. The level of the water in the vessel will decrease. But still, even in this case, something will be accumulated. Accumulation will not be equal to 0, but something will be accumulated at a given point of time. So again, accumulation is not equal to 0. And this condition is also unsteady state. We also call this as unsteady state. So these are some of the conditions that are applied in material balance questions or material balance equations. Most of the time you will observe that if a question does not explicitly, that means does not directly mentions that there is a steady state or unsteady state, so you have to assume steady state in that scenario. If the question does not mention that the state is unsteady, then you will assume that the question presents an equation or the question presents a problem about a steady state. You have to assume that by yourself. Okay, so you have to assume steady state. That means inflow is equal to outflow. You will have to assume that by yourself if the question doesn't mention it. Now let me just quickly mention the steps that are required to solve a material balance equation. Steps to solve a material balance, you can say problem as well, you can say question as well, or whatever you want to mention. So the first step is to collect all the data that is given in the question. Alright, after you have collected all the data, what you will do? You will draw a block diagram. Okay, if you draw a block diagram, you have to make sure that you draw it with system boundaries. I'll just explain in a bit that what are system boundaries. The third step is to annotate all the data. And the fourth step is to select the basis to solve the question. I'll just explain all these steps one by one, so don't worry about that. Now the fifth step is to write the equation for total mass balance and component balance. And finally, you will have to solve the equations. Now let's look at these steps one by one. What do I mean by these steps? Now, first of all, you have to collect all the data. That should be obvious. If any numerical problem is given, you have to collect all the data. After that, you have to draw a block diagram and the system boundaries. Now, what do I mean by a block diagram? I just illustrated in the beginning. Let me just scroll up and you will remember it. So this is a block diagram. Evaporator, crystallizer, sugar solution is flowing in, a final product is being collected, water vapors are flowing out. So this whole diagram, you can call this as a block diagram. Now, what are the system boundaries? I didn't draw the system boundaries, and the system boundaries can be depicted something like this. Let me draw the system boundaries. What do I mean by that? So the system boundaries can be something like this. Okay. Now, why do we draw this boundary? What's the purpose? I mean, we can also solve this without drawing a specific boundary, obviously, but why do we specifically draw it? We specifically draw it because to involve all the arrows or to involve all the components that are entering into the system. Not only we draw a system boundary or this dashed boundary outside the whole block diagram, but we also do this for specific components. Now you will observe in the material balance questions that there are specific components, like evaporator is one component and crystallizer is another component. When you combine all these components together, you get a total mass balance equation. So we have to draw the system boundary around these specific components as well. So I'm just drawing the system boundary around each component. Similarly, I will do that around crystallizer. Alright, so these are the system boundaries that have to be drawn. Now this will look a little bit cluttered because I hadn't planned that. I didn't plan in advance that I will be annotating all these arrows and I will be drawing the system boundary. But please make sure that this is legible and this is clear to you in your own notebook. And so these are the system boundaries. We have to consider system boundary for the entire block diagram, and we have to consider system boundary for specific component, because we may also be interested to understand the flow, inflow and the outflow for a specific equipment. For example, I may be interested as a food technologist, interested to know that what is the amount of water vapor flowing outside of the evaporator and what is the amount of concentrated sugar solution flowing outside of the evaporator. So I will have to draw a system boundary around that evaporator and then calculate the different components flowing inside and the components flowing outside for a specific given component. Same thing can be done for the crystallizer as well. So these are the two components, and this whole block diagram is the block diagram for total mass balance. Now let us move on to the third point. Now the third point is to annotate all the given data. Now what do I mean by that? Annotating all the data means if there is a block diagram or anything like that. For example, let's say that this is a bucket. Let's take the example of bucket once again. So annotating basically means that I have to mention different things or different components or different features of this bucket. So annotate, if I have been given that there is 5 kg of ice in this bucket, then I'll mention 5 kg around this bucket. If I have been mentioned that this is placed on a floor of a height 5 meters, then I will draw the floor and I will also mark the height as 5 meters. So annotating basically means displaying the data visually. So we have to annotate the data. I collected all the data, I made a block diagram, the system boundaries, I have annotated all the data. Now I have to select a basis to solve the question. Now what do I mean by selecting a basis? So in the question, it could be given, you may have been given the amount of time, you may have been given 5 hours for the time of inflow, or you may have been given 5 kg per second, that is the amount of any component flowing inside or outside per unit time. You may be given this, you may be given this, or you may also be given just the amount of mass that is flowing inside without the respect of time, without the respect of time, yes. So you have to select a basis. If there are different values given, different units given, then you have to select one basis and solve the equation accordingly. You cannot choose different components and put them into a single equation, because in a given equation all the units must be same. So you have to select one single basis to solve one equation. Now finally you have to write the equation of total mass balance and component balance. This will be based on law of conservation of mass, and if you don't understand what do I mean by this total mass balance, you have to apply the equation of inflow and outflow. Inflow is equal to outflow plus accumulation. You have to apply this equation here. Now if the question doesn't mention steady state, then you have to assume that A is equal to 0. And finally you have to solve the equations. So I think this video got a bit long because I explained each and every bit. But if you are interested to know about the numerical portions, how do we actually apply this in numerical portion, and how do we actually solve the problems of material balances, let me know down in the comments. If I get enough comments or enough requests, I'll make a separate video to solve the numericals for material balances. But you can apply these principles, all these principles that I just mentioned, to solve the questions of material balance or to solve material balance equations. Alright, so this was it for today. Let me know down in the comments if you have any feedback. I was using this software for the first time to make a video, so I really appreciate your cooperation if you are watching this till the end. Make sure you have subscribed to the channel so you do not miss any videos, any similar videos that come out. And I'll see you next time. Class dismissed.